Hi, let's continue our examples in which we are trying to apply Routh-Hurwitz criterion to determine the stability of different systems. And in this example, we have been given a block diagram and we want to evaluate the stability of the system. Okay, so the first thing that you want to do here is find out that system transfer function. And to find out the system transfer function, you have to write the output in terms of the input. So what is ys going to be in terms of the input? It's going to be g times 1 plus g times the input rs. Now g is the loop gain, which would consist of k and this transfer function here and any gain in the feedback. In this case, the gain in the feedback is 1, so we can just leave it out. So what we get is, if you do that, k s plus 2 over s times s plus 1 divided by 1 plus k s plus 2 divided by s plus 1 times rs, right? So what is the transfer function going to be? What is the transfer function ts going to be? Ts is ys over rs, and that we can write as ks plus 2 divided by s times s plus 1 plus k s plus 2. And we can simplify this and it becomes s plus 2 divided by s square plus 1 plus ks plus 2k. Okay, so in this particular transfer function, what is the characteristic equation? The characteristic equation is the denominator of our transfer function, which is this part. And we are going to form our Routh array using that equation and and then evaluate the stability. So let's take a look at that. So the characteristics equation of our system is given by this equation, right? And let's just form the Routh array, even though if you remember the previous videos, you know what is the condition for stability here. It is basically that all the coefficients of this equation are of the same sign. But even though we know that, let's just form the Routh array just as a practice and evaluate the stability. So to form the Routh array, what do? The first step is that you start with the highest power of s and write the powers of s on the left hand side of your Routh array. Then you fill in your coefficients in the first two rows. So you get 1 and then you get 1 plus k and you get 2k here, and you can write in a 0 here. Now what we want to evaluate is the value that would go at this place. Now to do that, what we do is we take uh, we figure out first of all which is our row of interest and which is our column of interest, right? So this is our row of interest and this is our column of interest. So we take the two rows that are above our row of interest, so which is this row and this row, and we take the first two elements of those two rows, so 1 and 1 plus k, and then we take the two elements in these two rows which are immediately after the column of interest, which means these two values. So we write 2k and 0 here. So our value at this point is going to be 1 over 1 plus k, so minus this, so that's going to be our value. And if you evaluate this, this should turn out to be 2k. Okay, so let me write 2k here. Now what is the criteria for stability? The criteria for stability is that these numbers 1, 1 plus k and 2k are of the same sign. Now we know 1 is positive, so The criteria for stability is that 1 plus k is greater than 0, which of course implies that k should be greater than minus 1. And another value also that we need is that 2k is greater than 0, which means that k is greater than 0. And if we combine both these conditions, we can see that the system is stable for all k's which are greater than 0.